So let's take a look at tuning a little bit more of a complex system. So I've just modified the denominator of this transfer function, which shouldn't really matter much to you. It's just, I'll just take my word for it, that's a more complex system. And let's just kind of take the same approach, right? Well, we'll just run it with all zeros just to make sure that nothing catastrophic happens. If something happens when you have zeros, then you've got a very complex system, or some sort of offset somewhere. So nothing happens. So let's kind of start ramping this up. Let's maybe start with just 0.1 again, and see what we get here. So we've already got this kind of overshoot behavior where it kind of bounces and then settles down. And we're trying to get to 1, and we're at 0.14, so that's not quite where we want it to be. So let's tune this until we get a reasonable settle. Even though we're going to notice this overshoot kind of increase, we want to try and get our settling point to at least be close to 1. So let's kind of start ramping this guy up here. Alright, we're at 0.4, so maybe we'll see it's going to be kind of around 1 again. We'll see. Right, we're at 0.6. Let's try 1.5 and see how much further that brings us up. 0.7, but we're really getting a big peak there, so maybe I'll keep that at 1 again. And now I want to start tweaking with my KI. So that should bring us better to our actual set point of 1. So let's add a little bit of that and see what happens. Just a little bit of integral term. And so it does get to 1 now, except for it takes 120 seconds. So it's taken a while to get there. The integral's working, it just takes a little while. So let's give it a little bit more integral gain. And now it's taken 14 seconds. And this is where you kind of also want to think of the significance of the step response, or the significance of the way this curve looks. So if this is like your car in its cruise control, and you're gonna accelerate, and then it's gonna kind of jump down and bounce around, and that might not be something you want. It might be acceptable for something like temperature if it bounces up, as long as it doesn't overshoot and it kind of takes a little while to settle. That might be fine, but for physical systems, you have to be conscientious. Woof, can't say that word. You have to consider the effect that those waves might have, right? It's going to translate to vibrations in mechanical systems, so that's something to really consider. Anyway, let's just keep ramping this up and observing the effect. The nice thing about doing this as a simulation too is we can test values and just kind of willy-nilly pick things and see what happens. So we see here that we are overshooting now. And that's going to be inevitable due to the nature of the system that we're controlling, is we're going to have this overshoot with just using KP and KI. So now what we want to use is our derivative term, and that will actually kind of ease this overshoot here. So let's kind of add a little bit in there and see what that does. So yeah, our overshoot is a little less, which is good. Let's add a little bit more in there. Let's maybe go to 0.3 and see what a derivative of 0.3 does for us. Yeah, so now we're not overshooting at all. We've got a little bit of a hump there, and it's taken about 9 seconds to really get there. Let's try a little bit more and see where that puts us. It would be nice if we could have a smooth curve, because for some reason I'm just kind of envisioning this being a cruise control system. So there, it's taken 5 seconds, and it's getting there. Maybe we can go a little bit further and see what that does. We don't want to go too far over, because we can start getting crazy things happen. So look at, even here we went too far over on our derivative, and now it's actually taking more time for it to really settle. So it looks like Looks like 0.5 might have been our kind of happy zone for that. Uh, and it may be valuable or it may be worthwhile to go back and test test and see what happens if we maybe increase KP a little bit or KI. So let's do that. Now that we've got this KD in here, because this is everything kind of interplays together, and so when you change one, the whole game is kind of changed. So even though 1.5 KI didn't work for us before, now we've got a derivative term in there, and that might kind of interplay and counteract one another. So let's up this and see what happens. That looks considerably smoother, right? We're 4 seconds, and this is a nice smooth curve. Let's maybe let it ride and see if we have a little bit more KI term in there, if that helps us out. So now we've got overshoot, so we got greedy. And last but not least, let's try and increase our KP and see if that can decrease our time at all. Yeah. So the time's about the same, and we've got a little bit of oscillation in there. So let's actually just take that out. And I think this looks like a decent response. Now, your response it really depends on your system. So that's when experience kind of comes into this, and knowing that something's going to take a long time for it to respond. Something should be able to respond quickly. Like motors should be able to respond quickly, enabled in terms of like being able to get up to speed. But something like temperature is the example that I always think of. That's something that's usually pretty slow. Like if I'm heating my house, if I change my thermostat to a certain temperature, it's going to take a while for that to actually have an effect. So a long time to get to that set point is reasonable. So that's just kind of about knowing your system. But anyway, so this was an example of having to use KP, KI, and KD, and you saw that we had to play around with it. We had to tune it. And now this isn't necessarily how a quote-unquote controls engineer would solve this problem, right? They've got a lot of tools in their toolbox that they can use to analyze their system that they're controlling and be able to essentially calculate what these values should be. But for someone who's just kind of utilizing a PID algorithm once in a while, it's kind of suitable to just be able to know how to test and tune these. And when I say test, that's kind of also a more difficult point, because testing these, if you have it on a physical system, if it's something like a small robot arm, that you could like lift up, that's not that big of a deal. But if it's a big robotic arm that's made for lifting cars, that's when you don't want to have accidents, and that's when you don't want to have your curve vibrating, because that could be substantial. So that's usually when you want to step up your game and learn a little bit more controls to make sure that you can really analyze your system and with pinpoint accuracy find these coefficients.